we're having basically these dimensions. This is a magnetic core, and I'm asking you to basically, based off of these numbers that are given, we're asking to find out the length of the core, the cross-sectional area, reluctance, basically reluctance in the air, the total reluctance, phi, MMF. So what is given is number of turns, the mu r, mu zero, the dimensions, and we're asking for the current if B is equal to 1 Tesla. So you can see that B is given. If B is given, then based on these dimensions, we want to find out the current, which should be really easy to do because in terms of the L of the core, you already know how to find that. We take the average of the length, and then based on the dimensions, the cross-sectional area would be easy to find. And then the reluctances of the core, the air, and the total reluctance would be found. And since phi is B times A, where A is the cross-sectional area, then also given the fact that your MMF would be the R total times phi. Yeah, so when you have like the circuit, if you have the reluctance, this would be your MMF, and this would be your phi, right? So your MMF should be equal to R times phi. And from the other side, that MMF is equal to N times I. So from here, you should be able to find the unknowns. All right, so this is talking about a circular loop of wire, which has a certain radius and a certain, basically, impedance. And this is placed in a time-varying magnetic field perpendicular to the plane of the loop. So it would be something like this. If you have like a circular loop like this with a certain radius. So in this problem, it's 2 meters and a certain resistance. So R would be 5 ohms. The radius is 0.2 meters. So this is the plane of the loop. So let's say there is a field that goes into the page, for example. We're putting that loop inside this magnetic field. So B is going into the page. The magnetic field varies according to this equation. So we have a B of t, which is equal to 0.5 t squared plus 2 times t. So it's a time-varying magnetic field, as you can see. B is in Tesla, t is in seconds, okay? We want to find out basically the area of the loop, which should be easy. So that's the area of the loop is just pi r squared. And then we're asking for the induced EMF in the loop at time equal to 3 seconds using the Faraday's law. So how would you find that? We know that based on the Faraday's law, dE would be d lambda over dt, right? D lambda over dt. Lambda is the flux linkage. And in this case, flux linkage would be the same as the flux because there's just one loop. So that would be e phi over dt. But what is phi? Phi in this case is B times A, right? So since A is constant, so we would have d of BA, right, over dt, which really becomes A times dB over dt, which in our problem becomes A times, what is dB over dt? That's 2t plus 2, right? So it really depends at what time. So E is a function of time. E of t would be 2t plus 2 times A. And you can find the induced voltage based on that. The current which is flowing through the loop at t equal to 3 seconds. So how would you find the current? So we would have a voltage induced with a certain basically plus minus. So if the current should be going this way, right? the current should go this way, because if the current goes this way, the resulted basically magnetic field would be opposing the magnetic field which goes into the page. Isn't that so? So this should be the positive, this should be the negative, and this should be our current. What would be the current? The current would be the voltage divided by the resistance. So whatever voltage we found, we divide that by the resistance, we would find the current. The power dissipated, so the power that is dissipated would be, so the current would be equal to E at time, at whatever time, that would be a function of time as well. I of t would be E of t divided by R. And the power that is dissipated, that is also a function of time, and it's equal to R times I squared. Now, if we are basically reshaping this loop in the form of a straight wire equal to the circumference of that circle and place it in a uniform magnetic field of 0.4 while carrying the same current from part B, we want to find out the force on the wire. Okay, so this is really another problem. This says that, let's assume you have a bar which has the same basically circumference, the same length as the circumference of this, which is how much? 2 pi r, right? So this is the length, the length of that wire. And then we're putting it in a uniform magnetic field of 0.4 Tesla. So here the magnetic field is constant. It's equal to 0.4 Tesla. While carrying the same current from part B. So the current that we found from part B was E at time 3. So E of 3 over R. So make sure you find that current at t equal to 3 seconds. We want to find out the force. So look at the force equation was, where force would be I L times B, where L's direction is the same as the current's direction, right? Okay, L and B are perpendicular, right? So it would be just easy to find. I E at time 3 over R times L, which is 2 pi R, times our external T, which B, which is 0.4 Tesla. And in these conditions, what would be the direction of the force? When you have like a external or a cross product, the first component would be index finger, the second component would be middle finger, right hand. Make sure you do it on the right hand. And the result would be in the direction of the thumb. So in this problem, we have a linear DC machine, which is consisting of a conducting bar of length L, moving with a constant velocity along frictionless rails. So a DC machine is linear DC machine could be as simple as a bar that you have a rail like that. And then it could move with, like this could be a train, for example. It moves with a V speed. So these are the rails in a uniform magnetic field. So let's say your magnetic field is into the page, FB equal to 0.3 Tesla. The bar is conducted to a DC voltage. So let's say we are connecting this to a DC voltage with VB equal to 5 volts. So this is V of your battery equal to 5 volts. And the resistance of 2 ohm. So the circuit has a resistance of 2 ohm. We want to find out the induced voltage in the bar. So how much voltage would be induced in this bar, in this connection, if you have an external magnetic field of 0.3 Tesla and a bar which is moving. When I'm moving to the right, how would be the changes of flux over time? Will it increase the flux over time or decrease the flux over time? Decrease, because yeah, the loop is getting smaller. This is the loop of the current that we have, okay, in here. And as you can see, if you move this to the right, this area becomes smaller. So therefore, the flux gets smaller. So you have to really increase the flux. Try to increase the flux. So therefore, the current needs to go up, which means that this would need to be the positive and this would be the negative terminal. So V and B are perpendicular, 2 times 0.3 times, what is your L? 0.5. So the result would be 0.3, right? So we would have 0.3 volts. And what would be the current, the resulted current? Find the resulted current by, now this 5 volt is against this basically. So you would have basically 5 minus 0.3 over the resistance of the path. So this is how you find the current. So VB minus E induced over dR. And then the magnetic force acting on the bar, now that you have a current, because of this magnetic field, there would be a current also forced on it. So that is coming from this I times L times B. So if you do the math, basically 0.3 would be the voltage induced. The current, resulted current would be 2.35. And then the force would be 0.3525 Newton meters. All right, so for this problem, we're asking for E induced first. So let's go to you want to find out how much voltage is induced. So E induced is V times B times L, okay? So what is in this figure? V is going to the left, so right hand, starting from the index going to the left, and then middle finger going out, okay? So the thumb is showing same as you can see, V times B, V cross. So this is the direction of V and B, okay? And then we're saying that the angle is 45 degrees. So it's important to note that V and B are 90 degrees apart. V is going this way, B is coming out. So the angle is exactly 90 degrees between those. And this angle is 45 degrees. Between V times B means this vector, and the conductor means here. So we're talking about a source in here. And then we have basically a path for phi, which would be divided into 2 parts. So wherever we have the same path of phi, we should consider all the elements there in series, right? We have a source here. We have one reluctance. And then this is going to the left side. And then we have the air gap on the left side. And then here we have on the right side and another air gap on the right side. So I believe we called it here L on the left. L on the left would be basically this whole section, right? Which is each of these are A plus B. So 2 times A plus B. 2 times A plus B is that. And then we have this path, which is, again, 2 times A over 2, which is A plus B, right? A plus B, and I just, this is basically A plus B, and I just subtracted this small portion, which is not really important because it's very small. You have to consider the fact that you have to take these 2 in series, and then these 2 in series, and then the results in series with this. So these 2 are getting in parallel, in other words. This is going to get into 2 paths. Call this phi 1, this phi 2. And this is, if this is like R1, R2, R3, and R4. So it's as if you're having a current source, having the source of I, which is going to be divided into 2 paths. So phi 1 would go through R1 plus R2. Phi 2 would go plus through R3 plus R4. So you know that this is a share of current, right? So phi 1 would be the share of phi times the reciprocal of the resistances. So for the left-hand side, you have to put R3 plus R4 in the numerator, and then R3 plus R4 plus R1 plus R2 in the denominator. And for phi 2, that's the same approach, or you can just say phi minus phi 1, which would be the same as phi times now R1 plus R2 over R3 plus R4 plus R1 plus R2.